Hello, my name is Nicole, and for this project I built a classification model to predict the presence of diabetes. Diabetes is a condition that can be very difficult to manage, and there are often obstacles in predicting and preventing this condition, especially with those who are more likely to develop it. And many people find themselves developing it throughout the course of their lives. The good thing is that there are many factors that can help indicate an individual's chances of developing diabetes and predict the presence of diabetes. The overall goal of this project is to create a classification model that predicts the major contributing factors leading to diabetes and determining if an individual has diabetes or not. The dataset that I chose was a diabetes set from Kaggle, which contains information about people diagnosed with diabetes along with their demographic, medical, and clinical history. I believe that this dataset would be a valuable source to carry out this project for studying diabetes management, risk factors, and predictive modeling for the outcome of diabetes. The dataset contains two files shown here, the testing CSV file and the training CSV file. There are a total of 9 variables that could be seen here: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, and outcome. The target variable here is the categorical variable outcome. The categorical variable outcome has 2 levels, 0 for no diabetes and 1 for yes diabetes. There is a presence of diabetes. In terms of data exploration, I began by looking at the dimensions of each file, the summary statistics viewed with the glimpse function from the tidyverse package, identified and removed outliers, calculated correlation between variables, conducted collinearity and chi-square analysis, evaluated data distribution, and created multiple plots for visualization. I created 4 plots to visualize the process of data exploration and data distribution. I believe that these 4 plots presented insightful information regarding the major contributing factors to diabetes. I also did a bar graph, as you can see here, one showing the variable correlation with the outcome of diabetes with and without outliers removed. After removing outliers, we can clearly see that the correlation of the BMI variable decreased, helping us attain a more reliable result for further analysis with these values. When looking at the correlation values amongst all features against the outcome variable, seen here, we can clearly see that the variables with a moderate positive correlation with the outcome of diabetes is glucose and BMI, while all other variables still have a positive correlation with this condition. To clean and reshape the data, I identified any missing values, and in this case, there was no missing values. However, I continued with the process of imputing them as if they were present and normalized and standardized it with the Z-score scale. For my feature engineering, I engineered the BMI category feature function, which I believed would provide valuable insight into identifying the major contributing factors of diabetes and how the BMI correlates to that. The feature divides the BMI variable into 4 categories: underweight, normal, overweight, and obese. In this first bar plot, you can see the distribution of individuals across all BMI categories, and it's clear that the majority of individuals fall under obese, followed by underweight, normal, and underweight in descending order. The second bar plot shows the distribution of diabetes outcome across all categories, and we can see a significant increase of the presence of diabetes in individuals classified as obese when compared to the other category ratios with the outcome variable. I also performed dimensionality reduction with the principal component analysis. The three classification models that I selected was logistic regression, random forest, and support vector machine. I chose the logistic regression for Model A because it works well with binary classification tasks, like this case predicting the presence of diabetes. And I trained the model with the train function from the correct package and specified the outcome variable to all the other variables as predictive features. Then I set the parameter to GLM from the stats package for logistic regression and the family parameter to binomial to indicate the binomial distribution for binary outcomes. I chose the random forest for Model B because it can work with data sets that have more complex relationships between predictors and the target variable outcome. I trained the model the same way as Model A with the train function from the correct package and specified the outcome variable again to use all other variables as predictive features and set the parameter to RF for random forest. This algorithm is good because it can see nonlinear relationships between variables due to its ensemble capabilities and combines multiple decision trees to improve prediction accuracy. I chose the support vector machine for Model C because of its ability to handle nonlinear relationships and outliers. I trained the model with the train function from the correct package as well and specified the outcome variable to all other variables to predict the features again and set the parameters to SVM radial for the support vector machine. This algorithm is good for binary classification tasks as well, in this case predicting the presence of diabetes, and can also handle complex relationships. To evaluate the models, I created confusion matrices, evaluated multiple matrix, performed the holdout method evaluation, k-fold, cross-validation, failure analysis, and compared all the models. When creating the confusion matrix for the logistic regression, the logistic regression had an accuracy of 75.45% with the true positive rate of 62.94% and a true negative rate of 83.33%. For the confusion matrix of the random forest had an accuracy rate of 95.68% with a true value rate a positive rate of 92.94%, a true negative rate of 97.41%, and the confusion matrix for the support vector machine had an overall accuracy rate of 80.68% with a true positive rate of 64.12% and a true negative rate of 91.11%. When extracting the metrics from each model, and performing the holdout method evaluation along with the k-fold cross-validation, it's clear that the random forest model shows the highest accuracy, precision, recall, and F1 score, reflecting its great performance in obtaining both positive and negative instances effectively. The logistic regression model performs well, but it was outperformed by the random forest model, and the support vector machine model shows a slightly lower performance than the random forest, but it still achieved good metrics throughout. However, for this classification project with these three models performed, the random forest model appears to be the most suitable choice for this dataset. I created the function create simple to create a simple ensemble model, which is create ensemble function to build the ensemble model by combining predictions from the three models. The predictions for each model were added using a simple majority voting approach, and the predictions were binary, 0 for no diabetes and 1 for the presence of diabetes. I then applied the ensemble model to the validation set to make the predictions, and the accuracy was calculated by comparing its predictions with the actual outcome of the validation set. The ensemble model didn't perform well and achieved an accuracy percentage of 38.64. And when compared to the other models individually, the logistic regression had 75.45% accuracy rate. Random forest had 95.68% accuracy rate, and the support vector machine model had an accuracy rate of 80.68. The ensemble model accuracy is almost half of that of the logistic regression model, and it indicates that combining these three models would not be beneficial for predicting the presence of diabetes in this data set. In summary, this project used the machine learning to predict diabetes with random forest model, demonstrating the highest accuracy among all the other models, including the ensemble model. This highlights the importance of selecting the most suitable model for any task, in this case, detecting the major contributing factors and presence of diabetes. Some of the key takeaways that I took from this project was acquiring the data processing to optimize the model's performance, exploratory data analysis that can provide valuable insight to data sets and help guide decisions on feature engineering and modeling, the importance of selecting appropriate evaluation metrics to adequately evaluate the model performance and data interpretation, the importance of organizing your code to make it understandable by those who aren't even necessarily in the data science field. And I appreciate how this project highlighted multiple aspects of data science and how impactful machine learning and data mining is to obtain valuable insights through problem solving and modeling. This is the end of my presentation, and I'm very grateful and happy to have learned so much in this course. Thank you.